PyDataDC. And we're hosting this today, co-organized with Statistical Programming DC. And before I mention that, I want to kind of also introduce you my co-organizer for PyDataDC. It's Anuj.
Good evening, everyone. My name is Anuj Patworthan, and I'm the chair of the organizing committee for PyDataDC. First of all, thanks a lot for coming. Really appreciate you all being here. Something I'm excited to let you guys know about. Unfortunately, none of this is completely finalized or official yet, but I'm very excited to say that hopefully, and be on the lookout for this on your calendars, we're going to bring PyData to the DC area this fall. And so we're hoping that we'll have full-scale PyData event, all 3 days, later this year. So be on the lookout for that and more information. But my kind of request for you guys who might be interested in the broader community, whether it's kind of just to share the event and promote it, or just to be on all the right listservs, or to actually help us come up with the best way to make this the best conference we can make it. Please do, whenever you get the chance, if you're interested, reach out to the organizers of the meetup group and get in touch with us, and we'll kind of make sure you're added to the appropriate levels of engagement and kind of get anyone who's interested in being involved and helping be a part of this. So I'm super excited about that. I'm looking forward to hopefully meeting you guys soon.
All right, thanks, Anuj. And I want to say, leading up to the conference in October. There we go. Show of hands, has any of y'all, how many of y'all have been to a PyData conference before? All right, awesome. So hopefully they'll change to be a lot more by after this October. Now, leading up to the conference, we want to do a variety of co-organized events with other meetup groups in the area to put some local interest in this. And the most welcoming of it has been Statistical Programming DC. So I hand over to Mark to say a few words about Statistical Programming DC.
Hi, good evening. I'm Mark Weissman. I am co-organizer of Statistical Programming DC, which is a part of a broader organization called Data Community DC. Raise your hand if you've heard of Data Community DC. Okay, so most of you have, so great. For those that haven't, Data Community DC was started about 3-4 years ago. We're an umbrella organization, and really our focus is to promote kind of data professionals across the entire spectrum. So our meetups range from data wrangling all the way down to statistical programming, data science, data viz, data business, et cetera, et cetera. So we run events usually every month. So the Stats Programming DC group, which used to be the R group, we actually changed the name about 3 years ago because we were doing a lot more Python events. So it's just really natural that we're kind of helping PyData DC get off the ground. And I wouldn't be surprised that PyData DC is going to be part of the data community family at any point in time soon. If we'll see how that goes. But I'm really excited to have this. I'm also helping out kind of with the PyData organization, and we're looking forward to that kind of event. But I just want to introduce Sean, who's the president of Data Community DC, also one of the original founding members. He's going to say a few words. So thanks again for everyone coming out, and please support Jim and Anuj with the PyData DC, and we're going to hopefully see this grow and flourish like all the other groups have.
Thanks. My name is Sean Gonzalez. I know a few people in the audience, and as for joining, we're working on tools to make finding speakers and sponsors easier and making find venues easier. It's all part of a service that we're trying to put together. We're currently in the process of raising money for this. We're also introducing an event introduction service. People come here looking for jobs and looking to find other people. Majid might make an announcement here in a second about looking for a job. He's been to every one of our events looking and meeting different people. And we're not recruiters, and I have no intention of being a recruiter. So we have to formalize this process because I don't go around remembering exactly how this person relates to this other person, and I certainly don't want to spam people on LinkedIn. So what we're doing is, if you're interested, we collect your email address and what event you were at, and we put you in a candidate pool, and then companies can peruse the candidate pool, and you'll get contacted, you won't get contacted, and that's it. So if you're interested in a job, somebody that is associated with this network, come talk to myself or talk to Mark. He's the secretary of the organization, and we'll be sure to get you into that candidate pool. Thanks.
I want to actually take this section to ask if there's any announcements anyone would like to make, whether it's other meetups or anyone that has looking for folks or looking for jobs
Oh, that was me.
or hiring. Yeah. There you
But you spoke for me already. So.
This guy's really smart. He's just being shy right now because I called him out.
So he went to it, he's looking, and he's great, so we'll talk to him. Just two announcements,
Doesn't even need a
related
name.
but unrelated. One is, we have a stats programming DC event coming up at the end of the month. I just announced, put it on meetup.com today. It's with machine learning and R. It should be a great event. Rafael is going to talk about a bunch of different methods, and he's going to show code, like how to actually really do stuff with R regarding machine learning. Second is, I wanted to talk about the Kickstarter campaign that we have going for our educational partner, which is Data Society. Who here has heard of Data Society? Okay, so a few of you have. So for the folks that haven't, Data Society is actually a new company, an organization that really kind of grew out of data community as well. So the folks that organized Data Education DC meetup, Dimitri and Josh and Marav, they launched this company called Data Society, and they're doing online training. They're doing a Kickstarter campaign, and they're offering for the Kickstarter, they have a couple different levels. But basically, you get I think 1, 3, or 5, or courses like lifetime access to their offerings. So go check it out. The link. Do we have a bullet link, Sean? I'll come talk to me, and I'll give you the link.
You want to know what the Kickstarter link is?
Yeah.
It's just Google Data Society Kickstarter.
So that's it. So, any other? Thanks. No. Cool. No more announcements.
All right. Okay. Well, then I want to also take this chance to thank our sponsors. Actually, I'll use this one over here. NumFocus is the organizing committee behind all the PyData conferences and meetup groups. If you're not familiar, also sponsor a lot of open source development work in the Python community. I want to thank them for their contribution, and also Capital One for sponsoring food, and also Happy Hour will go afterwards for serving the spot. It's Capital One. I know you have that in Capital One.
Thanks for coming out.
Really good sponsors. Speaking of Happy Hour, it is a tonic, 3rd floor. We have the alcove areas reserved after this, so if you're interested, you can walk over. Tonic is only a block away down towards 21st. And again, I want to also say, if you're tweeting about this event, as a new organization, it'd be nice to get the word out and get some subscribers to PyDataDC. So mention PyDataDC and also the hashtag PyDataDC. And I wrote a script to see if anyone did that and pulled the latest tweets. So I haven't seen anyone on their phones because this has been wonderful. But I'll still try running it. I'm calling Selenium to go out to Twitter to search for the hashtag and then pull the results and run it through their widget JavaScript and save it to a picture that I'm loading it back. Of all the million ways to do it, this is probably the most convoluted way. So let's see if it works in the Wi-Fi that we have here. I'm not making Selenium run this minimized. And here we go, we have some results. And the latest tweet was actually from Casey. Like to
Surprise.
Thank you, Casey, I appreciate it. And others feel free to tweet about it as well. So that's it. Without further ado, I want to introduce Travis. I'm sure everyone in this room knows Travis as one of the primary developers of NumPy and also SciPy. He's also the CEO of Continuum, and we thank him for stopping by here to talk while he's in town. And I'm looking forward to the topic on scaling PyData. So Travis, welcome you to the conference. Yeah.
Is it on? It says it's on. I'm not sure if it's going to be closer to now.
Sounds on.
You might want to put it closer to it.
A little further. How's that? There, how's that? Is that a little better? Okay, we got thumbs up in the back. Good news. Oh, HDMI. Excellent. Oh, advanced. Okay. It's going to float out the session. And And it's a real pleasure to be here. I really want to appreciate it. Thank you for inviting me, letting me come. I was in town for another meeting. I really enjoy coming to these meetups. When we started Continuum 4 years ago, Peter and I also started the PyData kind of concept and movement. And when we started NumFocus, I started out with a bunch of, with Fernando, with John Hunter, with Terry Greenfield, really as a community-centric organization to really promote the grassroots effort that is the open source Python movement. At our company Continuum, we're really excited about the things we do there. But I'm also excited about just the community, and I wanted to make sure we built something together that we'd all be proud of. That's what we did with NumFocus. And so it's run by a separate board. I'm not on the board anymore. I used to be. Got it started. Fortunately, none of the people showed up. They're carrying it forward. I hired Rita initially, and now she works exclusively for the NumFocus board, and she's wonderful. She makes, they've got 3 people full time, essentially making sure that PyData continues to roll throughout the world. I think PyData Amsterdam is happening this week. We've got 9 PyData events this year that are happening throughout the world. And hopefully PyData DC will be one of them. It sounds like I know they're working hard on it. So thank you for being here tonight. It really is about the community and about people coming together to solve their problems. That's really what makes open source and an amazing phenomenon and to be a part of it. And I want to encourage you to continue to be a part of it. I'm going to talk today about something I've been caring about for a long, long time, and that's scaling the PyData platform. To me, that means NumPy, Pandas. I say PyData to encompass all of these open source software, this federated group of software that's written by a lot of people. I did spend a lot of time on SciPy when I was a grad student. I started that project just maybe to procrastinate my Ph.D., but ultimately, fortunately, it's got hundreds of developers now who actually can carry it forward. I've stopped actively contributing to SciPy probably about 2010. I did it for about 10 years, and then there's so many other things to do. And fortunately, there's a lot of people who carry that forward. NumPy I started a little later as a professor in 2006. I released the first version in 2006, and then until about 2012 was actively participating and helping the NumPy move forward. Of course, it now has dozens of developers and hundreds of contributors who are carrying it forward as well. So it's amazing to watch that happen. And then what's more exciting is to see, like, those are things I've been personally deeply involved with. Then I've had friends like John Hunter who created NumPy. And just, I remember in 2001 in SciPy, we were trying to have plotting. It was tough. There were only a few of us. And he shows up and said, there's this thing I wrote over the weekend. Over the weekend, but here's this thing I did. There's this beautiful plotting package that just took off. And that's what NumPy did. And then Wes McKinney in 2011, 2012 said, we need data frames. This NumPy array is great, but we need something a little nicer for Excel users, that's fair to our users. So what was cool is he convinced AQR to open source the stuff he was working on at work. And so it was really cool. It was a nice hack because all the other hedge funds who didn't open source their version of the same thing now are having to use Pandas because he got them to open source. So that's a good lesson for you if you're a company and they're not open sourcing things that aren't your critical value. I'm not claiming that everything should be open source. I think there's still room for some things that aren't necessarily, but infrastructure stuff, things that just if you want to be a part of everyday life, really should be open source. And Continuum, that's what we try to strive to do, is build as many open source products as we can while maintaining a business. When we started Continuum, we had 3 goals, 3 primary goals. I mean, the big goal is I wanted to produce more open source software. Fundamentally, that's what I'm trying to do, is create opportunities for people to work so that we can build more open source software that helps people solve data problems the way I think they should be solved, which is using array computing, or using vectorization, using the computer to its full extent. And I like NumPy, but of course after writing it and then after watching it get used, I saw there were a lot of problems, a lot of things I wish I'd done differently, things could be better. And so I was, how do we fix this? So we wanted to scale it up. We wanted to make sure we could take advantage of GPUs. We wanted to make it fast. We wanted to write compiled code. There are NumPy users here, although many people don't even know they use NumPy anymore. They're using Pandas, they're using X-ray, they're using something higher up the stack. How many people know about ufuncs? Raise your hand if you've heard that word, a NumPy ufunc. Oh, that's pretty good. Okay, awesome. Those who don't know what a ufunc is, it's just a funny name for a map, or a vector map across an array. An array is a container for a bunch of elements. And you often want to apply a transformation to every element in that array. And what a ufunc does, it gives you an object that has a kernel underneath that will apply to every element that way. Ufuncs are great. I was probably one of the only ones who wrote them in 1999. My first module, in fact, for Python was an extension called special, which brought in array functions and Bessel functions, made them ufuncs. To make them, you had to write C code. And it was kind of painful, and not many people did. And it was in fact, my very first contribution to NumPy was actually the documentation for ufuncs in numeric, in a book co-authored with Paul Dubois and David Asher and Conrad Hinson and a few other folks who helped numeric come along after Jim Huguenin originally wrote it. They went off to do great, bigger, better things as well. But ufuncs have always been, you have to write them in C, is a pain, because I've always wanted to write them in Python. But to really get there, we had to write a compiler. So that was one of the first things I wanted to do when we started Continuum, was got to get a compiler for Python. So, and that's a whole long story, and I'll tell a little bit about it to go on. But I want to talk in this talk about scaling. That was a big part of what we wanted to do with the Python stack, with NumPy and Pandas. The other part, so scaling meant compiling machine code, including the GPUs that were coming out, the many core sister systems that were coming out. So of course, everybody's heard about the GIL, and now, oh, Python has released the GIL, so Python's not good for programming. If you're a PyData user, you know that's nonsense, because NumPy, SciPy, all the analytics stacks release the GIL, and you multi-threaded analytics with Python just fine. It's not a problem. In fact, it's nice to have a place where you know the GIL, that there's only one thread at a time running, so you avoid race conditions, and threaded programming can be hard. So we wanted to scale it up. The second thing we wanted to do was build, in 2012, the Hadoop club was starting. All the enthusiasm over Hadoop, all the enthusiasm over MapReduce. Now there's some real good reasons for that enthusiasm, but at the time, none of it was realized. And the actual execution engines they had on Hadoop were really bad. But what they could do is store a bunch of your data. And so that was good. You could store a bunch of data in Hadoop, which couldn't really do much with it except MapReduce. At the time, even MapReduce is pretty slow. If you're coming from someone like me who had just done ufuncs and really fast execution on a big array of data. So it felt like, oh, what's going on over there? But you knew that parallelism was the future, that people were going to buy commodity machines and store their data and want to do execution on them. So one of the goals we had was actually scale NumPy to those machines as well. And so I'm really excited. I'm going to show you that we're doing that. It took us a little while. We actually now have a really good solution for scaling NumPy and Pandas. So I'm very excited about both the horizontal scaling and the vertical scaling. Horizontal means scale out. It means multiple machines going on a cluster. Vertical means getting a bigger machine, more memory, many cores. And basically, Anaconda, I try to say Anaconda because that's kind of our continuum story around the Anaconda platform, but the core capabilities to make this possible is open source, available to anybody in the PyData community. So it's scaling out the PyData stack. So basically what makes it possible for horizontal scaling is something called Dask and Blaze, and Conda plays a role because it makes it easy to replicate environments across those machines. And then you scale up basically with NumPy, and then a C++ library called Dask. I'm going to mainly focus my talk on NumPy and Dask. Questions?
Not a question, but can you just briefly mention the capabilities of all these products?
Oh, I will definitely. In fact, this is just introduction. So I'm going to talk about basically NumPy and Dask in this talk, a little more detail about those, and a little bit about Blaze. I won't have time to tell you about all the cool things you do at Continuum, because that would take another hour, and I would then explain OK, talk a little more about data shading, talk about some of the other projects we're in the middle of in the visualization story. But I wanted to first give you a little sense of how I view kind of Python and its role in this broader technology for data science story. Technology for data science really encompasses a lot of different capabilities, which is why it's, data scientists are in high demand, because essentially to be a great data scientist, you sort of have to have some familiarity with, if not expertise in, kind of a bunch of technologies. That's really hard. None of us actually know all of this perfectly. Right? We all have our strengths in kind of one of these areas or another. But Python is actually a common language between them all. That's one of the reasons it's powerful and it's popular. There are people in the Python society or the Python world that are web folks, or they are business intelligence or scientific computing. It's not the only one. We have here the statistical meetup, statistical programming meetup, because there's also R, and there's also, in fact, Scala and Fortran and C++ folks actually as well. But Python's a good glue language as well, even when you're using R, or using C, or using C++, or Fortran. So it really combines all of them. And with Anaconda, we actually support both Python and R, and really anything that can be packaged into a Conda package and shipped. Really, the foundation of Anaconda is really about taking the responsibility and the requirement to figure out all the dependencies you're trying to ship to somebody and make that much easier in a lighter weight way than shipping to a Docker image. You don't have to even know anything about Docker or images or anything like that. You can just know, here's my dependency tree, conda install this top level package, and everything else is installed as binaries. So that's kind of the point of Anaconda, is the platform for making it very easy for data scientists to do their job. And the key really is it's Conda package manager. If you haven't, many people use Anaconda. In this room, how many folks know about Anaconda or have downloaded and use it? Awesome, great. Maybe that's why I got with this. Otherwise you wouldn't, I don't know, self-selection. One of the great things about Anaconda is it just makes it easy to get all this stuff. And that was one thing we definitely wanted to do. We knew we were going to build a lot more stuff. So we had to make it easier to get the previous stuff. The NumPy, the SciPy, the pandas, and matplotlibs, because we're going to go build NumPy, Blaze, and DAS, and all the rest. But man, we can't get the original stuff, so it's going to be harder. So we made Anaconda free and easy and open to everybody. But the key actually was solving the problem of the dependency management. So not just get it once, what happens if you want to update it? Or, more importantly, the thing we see in industry all over the place is, what if I want two versions of the same package on one machine? Because one person wants to use a workflow that requires pandas 1.9, another person wants a workflow that requires pandas 1.8. Well, I couldn't force everybody to upgrade or downgrade to the same version. Now I have a fight, I have a conflict, because usually it's a dependency down here and they're up here, worried about their story. It just makes it that much harder. So with Conda, we said, look, let's solve it. Let people have more than one package on a single machine. And then they can share it very easily. I don't have to get a machine, I don't have to get an image, I can just create an environment very quickly, construct everything I need. As we did that, it's cross-platform, works on both Windows OS 10 and Linux, but it's also cross-language. There's something specific. We solved actually the packaging problem generally, not just for Python, because we talked about, it's really about library linkage and library relationships with each other, and solving the dependency management problem. So therefore, it's not just a package manager for Python, but also R and C, or anything else, actually. It's just a matter of who has created packages for those tools that you're looking for. So we have strong support for Python and PyData stack, and early support for R. We have an R Essentials package. Basically, we support people who are using Python and R together. We're not yet sort of going after people who use R alone, but maybe in a year or so we'll do that. So people are using Python and R, and there's a lot of folks doing that, and using R through the notebook. I'll tell you about Anaconda Cloud, just in case some of you may not know about it. It's a great place to basically put Conda packages, and if you don't put them there, others might have. So it's a place where anybody can host for free any of the Conda packages they've built. We provide about 800 different packages for people in our repository, but then we have to provide this location called Anaconda Cloud where everybody can put any package they build so that others can download and use it. Yeah. Trauma pit, that's a longer conversation. We can go into more detail about it. Yeah, the short answer is, it was horrible when we started Conda. It's gotten a little bit better since then, but we started PyData project. Guido came to the first one, and we asked Guido, hey, the package sucks in Python, what's wrong? What do we do? He said, no, close your eyes. Okay, so we did. Now then he went to assign somebody to be the package authority. Nick's a great guy, I like Nick a lot, but then they basically started working on the packaging story in Python to make it better. So the short answer is pip is not cross-platform or cross-language, it's just for Python. Conda works with pip just fine. You can Conda install something, pip install on top, it's fine. Conda merges environments and packages together, whereas in Python we'll do pip and virtual env. And virtual envs aren't as general as Conda environments. Virtual env solves the Python problem, not the R problem, not the Scala problem, not environments for everybody. So Conda is kind of more inclusive that way. That's maybe the, really Conda is more like a brew or a yum or an app kit or something. And that's kind of how we think of it. But it's more, we're trying to make it easy for data science to get their job done at the end of the day. And it has some crossover with other tools as well. But Anaconda Cloud basically gives you a PyPI, a place you can host your Conda packages. Anybody can host whatever they want. All right, so we can go into more detail afterwards. You have a question?
Can people have to know about things that are already in the cloud to use them, or is it a browser?
There's a search and there's a browse. There's a command line tool called Anaconda. You can Anaconda search for anything. Anaconda Cloud actually posts not just common packages, you also put fit installable packages up there as well, and R packages also. But they have different, so you can search for any of them. It's a general hosting facility actually for binary packages. And the browse, I would say the web interface to browse is not perfect yet, but you kind of have to know a little what you're searching for to use the search tool. But we keep working on that to make it easier. For now, the best use case is somebody's told you where it is, you know what you're looking for. So one of the things that we really worked on to make Anaconda scale was to take advantage of libraries that are already out there. The MKL is a math kernel library from Intel, long been known as a very fast BLAS and LA-pack. NumPy uses a vendor BLAS in order to get fast linear algebra. Oftentimes you'll see people go, well, is NumPy faster than MATLAB or MATLAB faster than NumPy? I saw that a lot for a while, and at the end of the day, it came down to, well, which kernel did you compile against? Which vendor BLAS did you compile against? They're both using that to get their speed. So it was more of a, did you configure it correctly? And you can configure NumPy to work against lots of different BLASes. In Anaconda 2.5, we worked with Intel. Intel is very generous. We have a very liberal license for Anaconda. You can take it, download it, ship it, include it, give it away, do whatever you want with it, distribute it all you like. Intel worked with us to basically allow us to do that with the MKL libraries that we're not shipping with Anaconda. So now Anaconda comes by default with MKL. You can disable it if you don't want MKL. Anaconda install no MKL and everything else goes away. But for now, it's there for free, the MKL libraries in Anaconda. It illustrates something about Continuum I'm very proud of, which is we always want to produce more open source software. But we also, as a business, have to sell something. So our policy as a company is we sell things on the cutting edge. We sell optimization, we sell enterprise pain point solutions, we sell things that help people get their job done with a desire to push things to open source and make them as freely available as possible. We've done that in several cases. Acceleration libraries that are used to be proprietary and are open source. There's another example. MKL used to be something we sold, now it's free. I would like to see that over the course of many years. We continue to do that for a long time. Python compilation, that's the first thing I would talk about with scale up, is how do I make Python faster? Lots of people will tell you, and you'll see all kinds of stories on the net about how slow Python is. And depending on your conversation, yeah, sure. Indirection, boxing things up, not using the machine code of the machine you have, is going to create some slowdown, especially for things like image processing, numerical computing, kinds of things that in the past we would all turn to C or Fortran for, and then link it to Python. But I wrote NumPy in C, right? So it was fast. Now with NumPy, what we've done is created basically a subset of Python that can be compiled to fast code. Now there are a lot of other compilation stories in Python. There's some really interesting ones. Of course, PyPy is one that's been around a long time. One of the things we do with this chart is show kind of, one thing that's really important for us is that we integrated with CPython. We weren't trying to replace the CPython interpreter. We're trying to make a new one you have to install. PyPy, currently, it replaces your Python installation. But that has some advantages, but it has disadvantages if you're trying to integrate a bunch of libraries together. Because all those libraries now have to go with you, and they don't currently. And it's sort of difficult to see how they would get there as well. So our compilation strategy, and others as well, rely on and integrate with CPython. NumPy does provide both just-in-time and ahead-of-time compilation. We can talk about that a little more. Many people, when we first announced NumPy, kind of blew their minds. Like, whoa, what are you talking about? If you step back a bit, I went to a Beasley course to talk compiler theory. I should have done that like 4 years earlier. Probably NumPy would be much better if I had. Compilers aren't that hard, really. Well, especially go back to parser or the code generator. But as a concept, you're taking the syntax from one language and moving it to another. So many of us are familiar with C, C++, or Fortran. That just takes syntax that looks like English or something close and moves it to machine code, usually through an intermediate representation. Now with NumPy, all we've done, we use LLVM. CLang uses takes C++ and C and converts that to LLVM, which is the intermediate representation, and then that library does the code generation. We do exactly the same thing, except NumPy takes Python code, Python bytecode, takes the bytecode, converts it to an internal representation, then to LLVM IR, and you get code generation. Something like this. At JIT, The JIT is the name that comes from the namespace, and you put it around your code. This one's particularly easy because it's taking arguments, then just run some for loops and return the value. But if you JIT that code, you basically produce this. You're not intended to really understand that. Just know there's some representation called an IR, intermediate representation, that LLVM then takes over and does the optimizing by itself.
I don't know if this place usually asks questions in the middle, but whatever.
I'm totally fine with that. That's the tradition we started. Let's do it.
So when I used to work with MATLAB all the time, they would say that, like, oh, we're going to have this thing that compiles MATLAB into C, so that way it's fast.
Yeah.
And then, because traditionally the algorithms guys would make some complicated thing and you give it to the software guys who would turn it into something we thought was incredibly ugly, but they thought it was elegant and graceful.
Yeah.
And, you know, they take a simple coordinate transformation and
Right.
break it apart. When we gave them code that was generated by the MATLAB tool sets at the time, they hated it because for various reasons that it didn't work with the hardware, that it wasn't optimized in any particular way. There was no way for them to fix anything. It was basically, you take what you get, you can't do anything with it.
That's right.
That's still the case.
For MATLAB?
Or,
I don't
well,
know.
you're basically talking about taking something that's human readable, translate it into a language that then it knows how to.
A little bit
Right.
different though,
It
actually.
sounds similar.
It does sound
while
similar, but it's a
ago.
little bit different.
Yeah.
Probably because the MATLAB compiler went to C. So nobody would actually claim that the LLVM-IR is supposed to be read by a human.
Okay.
Right, so that's one thing, is nobody would look at that and then start picking it apart. Well, I wouldn't have, maybe they might, but they'd have to be like really assembly language folks. This is a compiler, basically, so it compiles the code. The code is, you start with Python code, and it creates a compilation chain. There's no place where you're handing over to anybody and they look at it and try to think that, see if they can make it better, right? The compiler's trying to make it better. I mean, you could, at some point, start compiling LLVM-IR. There are other projects that take Python code and compile to C code. And there you can talk about, well, I can take that C code and look at it and then maybe see what it looks like. And you might have some, people would argue about that.
Right.
But, so I would say the answer to your question is yes, it's always going to be like that in some sense. Somebody's going to be able to pick apart something.
Right.
But I think in the Python world, it's actually pretty nice because currently, especially with NumPy, we're actually compiling scalar and array code. It's not that complicated yet. And so it's just starting to grow a little bit more complexity. This is an old example. I haven't updated it because you don't always have to specify the types, but it illustrates JIT can be called with no arguments, in which case it delays compilation until it's called, or you can call it with arguments, which tell the types of the input arguments, and then it can infer the output, or you can specify the output. In this case, it shows you the syntax, how do I declare a two-dimensional array? Use the colon syntax of Python. Say these are 2D arrays of doubles, so float 8 byte floats. But you'll notice in there are 4 for loops, right? And your Python Spidey sense will go out. You'll start to scream, nobody ever does that. You can't write for loops in Python like that. And you kind of should. I mean, if you're a good vector programmer, a vectorized programmer in Python, you go, I don't write code that way. That's true, unless you did it, unless you're compiling. If you compile code, it's fine with for loops. And sometimes, I'm actually somebody who recommends writing things in vector format, so NumPy does support a lot of the NumPy syntax. You can still write your code in vector format, it compiles it. But sometimes it's easier to write the for loop. So it's nice to still have, I cannot say that every time vectorized is the way. You won't have to write a for loop once in a while, especially when you're writing a map across a bunch of elements. So this slide kind of wants more detail. It goes into how NumPy works. It's actually pretty clever and fairly elegant. I'm really quite pleased with NumPy as a software project. It does some interesting things that to many people go, that's just magic. It's not. It's actually pretty straightforward, but it's sophisticated in what it does and to provide that kind of magic for you. But the point is it gives you machine code out of Python code, just as if you'd written C or C++ for a subset of Python. And you can't just, so it's a different take on it. And the SciPy team and the NumPy team, they sort of have different views on the world. Like SciPy's goal is to make sure it can compile every kind of Python you could write. Right? NumPy's goal is to compile the Python you would write as a NumPy person who wants to make something faster. To make it so you don't have to turn to C or to Julia or to Fortran or to something else. And you can write your code to stay in Python and have it be more readable but still get the speed improvements that you're looking for. So it doesn't require a compiler, it is a compiler, so you can get speed ups, and it supports a wide variety of tools. It also, because we're using LLVM, compiles the GPU. We'll see an example of that in a second. NumPy has 2 modes, so it's very simple to use, but it can be a little tricky to get sped up. If you basically just apt-jit your function, and you can apt-jit your function, sometimes go, well, this isn't faster, it might be a little slower sometimes. And if that's the case, it's because it didn't actually speed it up, didn't actually translate machine code, it just got rid of the interpreter in your back of what's called object mode. It's basically to make sure it always works. And you just get the Python runtime still there. So that happens. You don't get speed ups unless you're in this no Python mode. And you can explicitly tell it to go to no Python mode and raise an error if it can't, if you'd like. In fact, that trade-off kind of shows this how you use NumPy. You don't just put JIT on every function in Python. How you use NumPy is you use a realistic benchmark, look at the code, do some profiling, figure out where your hotspots are, figure out what's taking the time, and then JIT that or @vectorize. Those are the 2 entry points that are the most commonly used. @vectorize is the famed ufunc generating code that I wanted for a decade before we finally got it done. So incidentally, I tried my first @vectorize using the SciPy code base, which was really ugly and failed miserably. We got something working very, very badly, but that's what convinced me that we had to do it ourselves, because the goals were just different enough. We would never be able to do it with SciPy code base. So this is the basics. Here's an example of just writing a function and compact. Notice a couple of things. It can take NumPy syntax. You can use NumPy syntax. This assumes import NumPy as NP, as been previously written. So it's using np.mtlike, np.isNan. What happens when you say no Python equals true is it either makes machine code out of it or it gives you an error. So what this is telling you is that I'm using NumPy code syntax, but it's not going to rely on NumPy again. It's actually producing code that's independent of NumPy. It's basically constructing the mtlike function or the isNan function, but in machine code. We've got about, I think it's up to 60% of the NumPy API at this point, and the goal is to get 100% of the NumPy API. So basically, you can write NumPy code and get machine code out of it and then do element style, for loop there. It's kind of natural for loop for element in X, and an if statement. And then that produces code that if you test against it and compare kind of how you do the call in NumPy with fancy indexing versus that compact call with the check happening, it's about 3 times faster, maybe 2.x faster, 2.7 faster. Right, so it just illustrates how you can basically write NumPy-like code, put a JIT decorator on it, and get speed up. Sometimes 2 to 3 is not that uncommon against NumPy code. Now, in Python, you can then do things like you move that to GPU. You can talk about taking advantage of multiple cores, you can run this in parallel more easily. So here, this illustrates you can call other functions as well. And that often creates even up to 10x faster than NumPy because you're able to remove memory copies and you're able to inline code. So people here, anybody compilers have heard of inlining, what that even means? I mean, it basically means you don't have a function call overhead, even at the C level. You don't have the stack call overhead going to the C. It basically injects the code in the middle of the lowest level function. That's one of the tricks that compilers use to make things faster. LLVM does that for us for free here. So I have angle between, I've jitted that, and it's calling norm, and norm is a function that's jitted as well, and it calls clamp. And all of that happens, the clamp function's inline, norm isn't inline, but basically LLVM just decides. I don't worry about it, it just decides it gets to do that. So it's a very powerful system, and people are using it in production today to get speed ups. But it does have to be, it's not yet completely, just put JIT everywhere and it's just faster magically. You have to, but it can absolutely help you if you're writing array-based code to get things faster. We have examples, several examples now of with clients who are using pandas. One of the popular things now, people use pandas, they don't use it very smartly. They love the things like the magic alignment on the index, but that's kind of an expensive operation, and they end up doing that inside of a loop for 20,000 times instead of doing it once and then populate the array. Just little things like that. So we've done multiple times, we're taking some pandas code that might be taking 2 hours to run. With a slight refactoring, use NumPy at the right places to do the code, to do fast code across the data structure. get it down to literally a minute. Go from 2 hours to a minute, or even 30 seconds. So it's amazing when you see examples like that. You really can get much faster. Mostly it's a combination of people not knowing how to make pandas fast, plus speeding it up even more from there. So there's a lot of opportunity to use NumPy to make things faster. This is kind of a complicated example. I'll show a simpler example, perhaps of vectorize. This is just illustrating that your vectorize. What this does is take a kernel that's meant to run element by element on an array. So you write the kernel as if you're given one element of the array at a time. And it produces a function that takes arrays. Right? And what that function that takes the array does is take your compiled version that NumPy compiles and call it on every element of that array. So it's a nice kind of concept and mental model. If you can think of your problem that way, you can use NumPy to build very fast implementations of that problem. And it can also work in parallel really nicely too. And it translates to GPU very nicely as well. It's the easiest way to program a GPU. So this just illustrates something I tried, the SciPy special I talked about. I wanted to say, what if I had written this in SciPy special? I went out and found a bunch of libraries at C and Fortran and linked them together and put wrappers around them, spent a bunch of time. And I have a special function. It's awesome from Python. I mean, you look at the source code, it's a bunch of C, it's kind of messy, nobody wants to look at it. Right? I don't know what it is. So I basically just took the C code, translated it, kind of the concept, to Python, straightforward Python code. It's a bidet approximation, it's a rational approximation with some if statements and basically different approximations from different regions of the real line. Wrote those codes, you basically see there's two polynomial evaluations, one with a 1 in front, one with an arbitrary coefficient in front, so it can be as fast as possible, and a bunch of data for the coefficients of the polynomials. And vectorized that, and I got a result that was just a little bit faster than SciPy's. Except now the code's in Python. And then can be moved to the GPU more quickly. So NumPy's helping us scale up. It's part of the scale up story. It's very popular. Lots of people showing how I can use this to get 2x speed up even with the Python code on occasion. With a ahead of time compilation that was just recently added in 0.23 release. 0.24 just came out this week. But in 2.3, you can now ahead of time compile. So now you can use NumPy to build an extension module that you just ship to somebody. You don't have to have NumPy installed. So you can use it as a code generation tool to ship things to other people. There's examples of how to do that in the documentation online. I like to say that definitely SciPy and NumPy would be a whole lot different if NumPy had existed 10 years ago. My life would have been a lot easier. Your life would be a lot easier. We'd all be much happier. If we'd have done it this way. Right now, we're not going to go back and rewrite everything because that's just silly works. But new things can certainly use these tools and it all will work together just fine. So that's nice. We can release the GIL. Won't say much more about that, but that's a way that you can absolutely do multi-threaded code with Python if you use some of these tools. CUDA Python is one thing we did together with NVIDIA, basically showing how because we compile the LLVM, and NVIDIA uses LLVM as a code generator for their GPUs, we go straight from Python code to GPU execution. And there's two approaches to doing that. One is use the vectorize command and just tell it to target the GPU. And now you have a ufunc, the NumPy ufunc, with all the code executions happen to the GPU. That maps beautifully to the GPU many core architecture, where you're just running all those threads in parallel. It's also the fastest way to program the GPU I know of. So you can basically impress all your friends how you're using the GPU by running ufunc, Python kernel, put it over the GPU and get 10x speed up, even over the C code they wrote. Right? And meanwhile, they're struggling to see.
Is that being used with TensorFlow?
No, it's not yet being used with TensorFlow. There could be. Could be. Yeah, no, but CUDA Python it's CUDA, but you have to know the CUDA concept. You write kernels, you have to understand a little bit. It's a little harder to write CUDA Python, but you can, and people do it effectively, and there's lots of lots of training on this. Theano could use this. It doesn't because Theano started a couple of years before this project.
Could you specify the axis in the vectorized code?
Yes, it has more to do with the ufuncs themselves, like we do. Vectorize builds a ufunc. You actually have to specify the axis. You'd have to do it. You'd have to do it with NumPy shape. You have to kind of, or if you're doing a reduction, then you can specify the axis as long as you do a reduction. So maybe think if we went to a specific question, maybe it's good. And this just shows you can get 9 times faster. This is one final example just showing the Mandelbrot that gives kind of the CPython, all the different results. So the final scale up. This is just the Mandelbrot function, the kernel part of the function. You can run this a bunch of times to test whether or not something converges or not to see if the shape. Run this in CPython, that's 1x. NumPy, you get 13x faster if you use NumPy. Numba is 120x faster if you use Numba to compile. Now, if you take that and run it on the GPU to a CUDA JIT, on the GPU, you get another 100, you get 10, 20x faster than that on a Tesla K20. So, same code, run on multiple systems, you go all the way from 1 to 2000x faster. All right, lots of interesting things. There's a CUDA simulator actually, if you want to, because it's actually hard. The CUDA model can be a little hard. NumPy has a CUDA simulator, so you can actually debug your code in the Python land before you see it can run. There's a generalized vectorized. I love vectorized, but generalized ufunc is even better, because now your kernels can be matrix operations instead of just scalar operations. You can do all kinds of fancy things. And then Numba annotate can help you understand whether you're in object mode or no object mode, and figure out where maybe the type of inference is not happening. Lots of things don't work in terms of general Python. It is a subset of Python that's supported, so it's not like it takes all the craziness you might do in Python, which is great sometimes, but bad for performance. Lists and set dictionary comprehensions, recursion doesn't work, yield does work. You can make generators that compile with Numba, but you can't make coroutines. Yield from doesn't work yet. Modifying globals, debugging of compiled code. Once you compile that to machine code, people ask, well, how do I debug? The answer is you debug in Python first. So there are some things you can do with LLVM, but it's a little hard. It's harder. Support NP and the app decorator, or the app operator, excuse me, on Python 3.5. Support for some of the lineage is there, and then this generated jet function. These new smart arrays allow you to kind of automatically move from the CPU to the GPU. It's on the 0.24. All right, one thing I'll mention just happened in October of this past year is previously multi-threaded and GPU vectorization of ufunc was only available in our Accelerate premium product prior to October. We recently put it in the open source Numba just in October. So now you can do multi-threaded CPU and GPU constructs for Numba. Lots of progress, try it out. I've talked about Numba a lot in the past, so I'm going to leave it there. Happy to talk in depth with anybody. That was one of my babies when I started. I wrote the first version of Numba when I first started Continuum. Fortunately, they threw it out and built something better. But I have a lot of passion about what we're doing there because it's what I've cared about for a long time is scaling out, scaling up. I've also cared deeply about scaling out and how are we going to do this. And we struggle a bit with this. This is hard. It's a hard question. And I often compare it to the JVM. In the 90s, a lot of people wanted to make the JVM the place where analytics is done, and kind of that was rejected by a lot of practitioners who didn't want to do the numerics in the JVM. So a lot of analytics was done in Fortran, Python, R. A lot of other stuff was built C++, and an analytics stack was built up in Python. One thing the JVM got right and did very well was concurrency. And that concurrency concept, which they did right, led to the parallelization story, the Hadoop original MapReduce, following on the Spark execution engine. They have this really strong concurrency concept in the JVM. Python have this really strong analytics stack. And of course, what we all want is really strong concurrency and analytics. We want to pull together. And so I see it as two people climbing mountains, right? You have JVM over here, they're putting MLlib and all these kind of analytics stack on top. We're over here in Python land with NumPy and Pandas, scikit-learn, and lots of other things. TensorFlow I include because it's C++ native code. I call it the native code folks. We've got all kinds of execution things, but concurrency isn't that great. And that's what we want to do, improve the concurrency at PyData stack. So we started a project called Blaze, the same time we started Numba and Bokeh pretty early on. And its goal was to scale out the PyData stack. And it's still its goal, although what Blaze has done has kind of spawned a bunch of different technologies in trying to accomplish this ambitious goal. Right now, so in the end, Blaze is actually the highest level. Blaze is the highest level where you can just think about how your metadata and your expressions separate from the code to solve the problem of write once, run on mobile backends. If you today, when people would say, I want to do some analytics, first question they really have to ask themselves and answer is, where is my data? Because if my data is stored in CSV files, or it's stored on a binary disk, or it's stored in a database somewhere, or it's stored in a Hadoop cluster, I have to write code differently in order to do the analytics, the query. And that wasn't supposed to be that way, right? SQL was created in order to avoid that. So you all write one expression language and get the data. And SQL does help a little bit better. There still, it's all the vendors modified it. And in the Python land, people like to write pandas expressions and NumPy expressions. So what with Blaze, we wanted to build a system that let us kind of separate these concepts, not just separate code from data, but separate code from data from runtime execution context as well, and pull them together at the end. When you keep them separated, then you can talk about expressions that are independent of both code and runtime, and then they can be brought together at the end. And that's the goal of Blaze. So Blaze has join, group by, pandas-like operations, NumPy-like operations, and arbitrary data objects. Depending on where those data objects live, that's the backend it actually compiles to. And it has enough metadata about the data to know what kind of manipulation is possible, what kind of optimization is possible. Now, Blaze is still a work in progress. So if you're interested in Blaze, excited about Blaze, please come talk with us. There are some things definitely can be used out of the box, but it's not yet, I would say, in a state where I would say go out and just play with it and come talk to us, and we'll make it work for you. We're actually using it as a foundation for a product we're pushing out called, I don't know what it's going to be called soon, but call it Data Portal currently internally. But Blaze itself is an open source library, so it's got multiple contributors. Blaze really has this Triforce diagram to really promote this idea of expressions to be separated from the data and the metadata separated from the runtime and compute. Now you'll see down in the corner there, I've written a compute thing called DAS, because we built Blaze, we're sort of solving this general problem as well as, well, we need a compute runtime as well. And we have Spark, we have Impala, we have MongoDB, we have a relational database. Those are engines we can use for compute. But we needed a scalable compute engine for Python, for the PyData stack as well. And that's how DAS emerged, an actual scalable compute engine that can be used independently as well. It doesn't have to be used for Blaze, it can be used on its own. And then Odo is a little project we won't talk much about. It's a very handy little project because even though Blaze's goal is to not copy the data, you want to just basically write once, have the data sit where it is, have the code go to the data. The reality is certain code will run faster against certain kinds of data organization. And so the simple case for arrays is you have order, you have C order. You have row major or you have column major. Or you have a structure of arrays or an array of structures. So how the data is laid out makes a big difference in terms of how performant it is. So you're going to have to move some data around. You just want to minimize it. And only move it when you want to make speed improvements. So we're not going to solve the general problem of never having to move data around. But if you're moving it around, be intentional. Be intentional to go to a format that can be computed better. Odo helps you move data around. Odo basically is a copy command for data pointers. So you can copy from a SQL URL to a data frame. You can sort of this general copy command for data in a large number of use cases. You can go from a data in HDFS to a SQL table or a relational database. Very, very cool little tool. I'm going to skip pretty quickly around Blaze because it's not quite ready for prime time. It's definitely ready to play with and for contributors to continue to help us with it. It's going out, but it's going to come. We're pushing it to market through a product we have called Data Portal. We'll encourage you to use. And if you're a developer who'd like to jump in on Blaze, you're very, very welcome. What I do want to focus on, though, is how Blaze talks about data, because this is very important. One of the problems I think we have in the computing world is we've got 40 years of data encapsulation. Right? We're going to make objects and put all the data inside the object. That's great. It simplifies kind of messaging. I can just message and do something with that object. The problem is now I'm talking about big data, and my data volume is big enough. I can't be moving the data around. So I have a big silo of data over here, and it's only got certain methods that are available for it. And I have another runtime over here, another library over here that has other methods I want to call. Well, how do I use these methods on this data that's over here? Well, I have to copy it over there, right? That's kind of the concept. And the reason is because there's not a general way to talk about data. The data declaration, data description is buried inside of compilers and runtimes. So data shape is really an effort to take the concept we learned from NumPy about D-type, D-type is what allowed NumPy arrays to share their information with everybody in the stack of Python world. That was generalized a little bit in it's called PEP 318. It's an extension to the Python protocol in Python. Now memory views, and Python benefits from this way to talk about data in a way that doesn't cause memory conflicts. Some of you heard of the Apache Arrow project. Anybody heard that word? So I'm excited to hear about Apache Arrow because it's exactly the same concept. And so finally the world's waking up to what I've been trying to say for about 6 years, actually. It's not that. But it's not as general. So data shape is a generalization of what they're doing with Arrow by giving you a general way to talk about data at every point. And Blaze uses it, our C++ array library called Value uses it as a way to talk about data. So, sorry for the interlude, but data shape is one of the important things you've been doing in Continuum. It hasn't quite materialized in the tools you can use today, but it's coming, and it'll be there by next year. So this is showing you how you can describe and talk about all kinds of arbitrary data structures, arrays and structured arrays, columnar data. We'll have a data shape for Apache Arrow format. You'll have a lot of data shapes you can attach. The goal is you can attach any library, any capability library to any data. And if you get me later, I can go into great detail about the problem with the JVM, the problem with the loop stack, and how the JVM doesn't expose its memory well enough to allow lots of participants to cooperate. That's a longer story. So I'm going to quickly jump past that. But basically, the Blaze story is that you can layer expressions over any data. That's where we're headed. So basically, you have data, you have a way to describe that data, you can write expressions involving that data shape. Over here on this computer, and it goes immediately to this other computer. But what we're basically doing is exposing the guts of what SQL, what database engines do for you, that are hidden from you. Now we're making it possible for you to do that for all of your data on any scalable machine, kind of building a library to make that possible. And then to really help us get to the right once deploy anywhere for data and get out of the era of the 60s where we had to write code differently and we went to a different machine. We're there now. If you have data stored differently, you have to write different code to explore that data. I want to get out of that moment. All right. So I really want to spend more time on Dask. Yeah.
So how does Blaze get the data? Like, is that through select queries or?
It depends on the back end. It doesn't get any data, actually. Blaze is again mapping expressions over data. So it's much more like a SQL query does. How does a SQL get the data? That's sort of how I state your question. SQL doesn't really get the data. It takes the expression and pushes it to a database. So
how does it get at the data?
It basically depends on the back end. If the data is sitting in a database, it takes your Blaze expression and translates to a SQL query. Right? So if it's in Spark, then it takes your Blaze expression and runs PySpark.
So you're limited by SQL, by what SQL can do?
You are limited by whatever the back end where the data is stored, what it can do. Blaze is not limited, it can do whatever your back end is. Right? But yeah, you are going to be limited by whatever the engine of your data is. Our primary execution engine with Blaze is going to be the PyData stack, Dask. So you'll be limited by what the PyData stack can do. Like that's when we're done, when we're ready for kind of 1.0 of Blaze, that's what will happen. Is you can, as long as your data, you can handle code, push it to any database you want, but we're going to suggest, encourage you actually have it. It could be in files, it could be in a distributed storage, distributed disk, but in some place that the PyData stack can do that. Right? That question.
What around with that? You're running your own backend.
So kind of, yeah. So Dask is the first step there actually. What Dask gives you is this compute infrastructure, this compute that could allow. Basically, you could write a database backend with Dask now, and that's completely distributed. So what is Dask? Dask is a distributed compute. It's a parallel computing framework. Parallel computing framework. It leverages Python ecosystem. So rather than trying to reinvent it, it extends it. NumPy and pandas and all the rest. It uses blocked algorithms and task scheduling. At the end of the day, to parallelize something, you basically have to block it up and have to tap the scheduler, the task. That's what parallelism is. It's written in pure Python, so it's actually easy to contribute to, easy to interact with, and easy to jump in and help extend. The core idea is dynamic task scheduling yields the same parallelism. It's a simple library to enable parallelism. And then we have these containers, arrays and data frames, we'll get into more details, but it caps this functionality. And there's schedulers, including a distributed scheduler. So you can take the core ideas of Dask array and Dask data frame and run them at scale across a set of nodes in a cluster. So the core foundation of Dask is a directed graph, a directed acyclic graph of tasks. And they're going to show up all over the place. That's at the core. And it's a very simple specification of that graph. It's simply specified by a dictionary with keys and whose values are a tuple, whose first argument is the function call. So a Dask graph is very easy to specify. You can do it manually. You don't have to use any of the tools inside of Dask. You can build it yourself. It's very independent. It's a very simple, straightforward system. So it's easy to extend, easy to use. And the collections, build graphs, the collections are things like Dask Array, Dask Data Frame. Dask Array is a generalization of NumPy. It sort of has the NumPy API, but instead of immediately executing, it builds a graph of tasks, chunked tasks, do the work. And the data frame, instead of immediately executing, builds a task of pandas, does the actual work, so it covers. There's some others as well. And the schedulers are independent. You can write your own. You can use these schedulers, these are reference schedulers, they work pretty well. Distributed scheduler is getting a lot of attention and working better and better every day. But you can also, if you're IBM or you're Capital One, or if you're a big company, you figure you've got better scheduler engineers than we are, you might, then go ahead, you can take the Dask graph and schedule it however you like. So what I love about Dask is a very simple architecture. So that's what a lot of the Python community loves about Dask as well. That's why pandas, scikit-image, scikit-learn, have all have pull requests to support Dask in their systems. So it's kind of plugging into the rest of the Python PyData ecosystem in a emergent way, in a way that's sort of not because anyone's pushing it, because hey, this is a good idea, and that we all want parallelism, and this is the fastest, quickest way to get there. That's very nice. Basically the Dask array gives you out-of-core parallel ND array. So it's basically a NumPy array now that scales. And it gives you lots of operations. It's not a complete implementation of the whole NumPy API yet. It'll actually potentially never be a complete implementation because not every method of NumPy or not every function NumPy wants to call is actually scalable. So it's always going to be only that part of the NumPy code base that can scale, can be broken up in parallel chunks in a rational, movable way. So this actually presents a very nice kind of path where somebody can make an immediate connection to their data with NumPy or pandas, and then they want to make it scale. They can, well, I'll just switch to Dask. It's very simple, a couple lines of code change, and now you might find, oh wait, this call isn't there. Maybe this thing I'm depending on isn't actually scalable. And you have to rethink how you're doing the computation to put it inside of parallelizable blocks. So here's a simple example of Dask array with one. You can build ones. You have to say with Dask, because it's built a DAG, it doesn't compute immediately. Actually, you have to say compute to get the result. Otherwise, what you have is a DAG, is an array. So I have a couple of examples here. A little bit later, we'll play with it. Dask data frame is the same thing, except this is pandas. Instead of the NumPy array, you have data frame, which gives you a lot of operations, similar syntax, similar style, except now it's giving you a directed graph of chunks of tasks. And the data frame can therefore be much, much bigger than it could in memory. It can be distributed across a cluster of nodes. The actual data of the data frame can be distributed across a cluster of nodes. And the cool thing is it was much, much faster to get there because we're leveraging pandas already. The Spark world, they're building data frames as well. They know it's a good idea, but they're having to invent it, right? We're just basically constructing the chunking and using pandas underneath. So it's a lot simpler, and we're able to get a lot faster, a lot quicker. So we're leveraging the PyData stack. So here's an example of A as a Dask array, new operations, +1 times 2 to the third power. And it produces a graph. So you can see here, it basically split, it produces the graph based on chunk size. So one of the things you'll notice when you play with Dask array is there's an optional chunk parameter. And sometimes you have to give it the chunk parameter. What that is tell me how do you want to split this up? If you have this big array, how do you want to split it up? Because Dask is all about splitting it up and doing out parallel operations on these chunks. And once you do that, then every time you do a method call, it does the method call on all of them and builds this directed graph. It might come back together or it might not. And this is just a little GIF showing as you compute. There's actually a little OK plugin that can visualize the Dask scheduler as it's running. It's actually it's kind of nice. You can see Blue means it's done, data's ready, red means it's executing. And you see how it kind of finishes. Here's another more complicated example. We'll take B, I find the mean along zeroth axis, track it from B, add it to the transpose, standard deviation. It's kind of a more complicated expression. You can see that gets a little more complex, but it's still can be run. Yeah.
Do you plan on ever supporting recurrent relations, like for students?
Like a non-directed graph?
Well, cycles? Not
One with cycles? Not that I know of. You'd have to ask the DAS dev directly that question. Not currently, I'm not aware of any plans to support that.
So you wouldn't be able to scale up like machine learning?
No, I think you basically could do that by separating out the computes. I mean, a single graph may not be recursive, but you could certainly put it inside of an iterative system.
Okay.
Does that make sense? Yeah, I mean, but it's a good question. You can certainly ask the list. And of course, the graphs can get complex. This is actually showing how you don't have to use the containers to build graphs. The graph is a very simple dictionary of keys and functions to call, basically. So you can just insert your own and modify it on the fly if you like, and then hand it over to the scheduler. Each of these systems are included. This shows X-ray is a labeled NumPy array. It sits on top of NumPy, puts labels everywhere, kind of a generalization of pandas to n dimensions. And it's very nice for weather modeling and large array computing. It uses DAS under covers to allow us to do out-of-core computations and now parallel computations. I'm not sure if it's integrated with distributed scheduler or not in its API, but it certainly could. This just shows a simple example that was built a DAS graph that was used. This is a blog post that Jake Vanderglas. If you haven't read his blog post, we should. He's a very good writer. I actually see him as kind of if he's starting to write about it, it means, okay, maybe we're on to something here. So that's sort of just my own little internal, there's people out there I respect and go, okay, you probably did we'll do it. So and he's talking about it, it's actually pretty nice, and I can use it pretty straightforwardly to do parallel with Python. Now, the distributed key piece was a piece that, of course, I've been hammering for 4 years, trying to get its distributed capability. It took us a while because we went in a lot of directions and built a lot of code, but still, some of it's still to come in dying and data shape and some of the type system things that are emerging in what I would call the next generation of NumPy. But DAS distributed, it's very simple to set up and use. You can play with it at night. You can sit on your laptop, you can put it on a cluster. Matt Rockland is blogging actively right now about how to use this. So you can go to his blog, and Matt works for us, and we work closely together. But there's a lot of work happening right now to make this popularized, help people understand how they can use it. My goal is that by the end of the year, I would like everybody who's using PySpark has at least tried DAS to see if it's actually better for them. We have some benchmarks that clearly show DAS is about 10 to 100 times faster than PySpark on array computations. If you're just doing lists and word counts on things that don't need array computing, then PySpark's 1 to 2 times faster than DAS. Right? So Spark does well on some of those things. If you're doing array computations, you're building a Pearson array coefficient, you're doing computations on arrays, DAS goes faster. And that's sort of not too hard to understand, not too hard to believe. So I'm very excited by that because we always knew we were leaving stuff on the table. People were leaving on the table performance when they're trying to kind of take the whole of PyData and jam it through the Spark ecosystem, which wasn't really built for the array computing that Python had. And so we wanted to kind of make sure and understand what's possible if we just do a Pythonic approach. So very excited about it. Those numbers are still early. It's very early, not early stuff. Those are our first early benchmarks. So we talk about them generally, but they'll come out and we'll start to see, and people will start to explore this over this year and prove to themselves what works well. I'm also very excited about this initiative called Anaconda Inside Hadoop, or PyData Inside Hadoop, if you're just in the general community. What it allows is part of the DAS project. So because of these efforts, these initiatives, we've actually taken DAS, which used to be part of the Blaze organization that spun out of Blaze, and we now have a DAS GitHub project. Its own organization of GitHub called DAS. So people can just use DAS all by itself. And inside of DAS is this idea of we can connect to distributed runtimes. We can connect to a lot of people have new clusters out there, and maybe they want to try using DAS. Well, their data is HDFS. So they still need to read the data from HDFS, and they've got a scheduler that uses Yarn or Mesos, and so we've got to connect to that and somehow allocate our D workers using those mechanisms. So that's what the Anaconda side of Hadoop effort is all about, is connecting Dask to Hadoop clusters. Dask can be used on any kind of cluster, any kind of runtime. It's not tied to Hadoop, but it certainly can be used with Hadoop. And that's what this makes possible. It's I say it's the native way to do Hadoop on Python. It's it's the way, it's the right way to do Hadoop with Python. Go ahead.
Are you guys doing distributed methods already? Is it positive or is it?
So the project is actually Yarn Mesos integration is really about it's independent of distributed, right? Yes, they're working together. So currently Yarn is supported. Mesos, we're in early conversations. We'd love to support it, but we
Map archives?
no, we're happy to collaborate with Map Archives. Happy to collaborate with anybody who helps us. The project's called NIT, and I'll do the next one. So I believe it's better than Spark. Really, it's general availability coming in about April. Right now, you can get a hold of it, you use the code, but it's still going to be worked on, and it'll be still be worked on throughout this year. Again, my goal is by the end of the year that I want anybody using PySpark to basically. I think a lot of those folks will be switching to Dask by then, depending on, of course, other inertial factors. But for new projects especially. So the two key libraries really enable this PyData inside Hadoop connection. The reason I say inside Hadoop, beside Hadoop, is a concept that comes from kind of, are you inside the database or are you outside the database? Anaconda and the Hadoop ecosystem can always stream data from Hadoop. It's always been all possible to do that. But what this does is allow you to go to the data directly. And you're an executionist. You're a first-class citizen in the execution framework. So you don't have to talk about Spark and Python. You talk about now just Python. Talking to the data, talking to schedulers, and do it all. That's what's right inside. You're right there. And with this tool, you can absolutely build a distributed database with this kind of capability. We don't have that on our roadmap, but we'd love somebody wanting to play with that and see what they can produce. The two key libraries, these are open source libraries, please. They're open for collaboration if you can jump in and help. One is HDFS3, which is a Python wrapper to Pivotal's Live HDFS, which is a C direct native reading from HDFS library. So HDFS3, and then you can see the docs there, and then NIT is the other one. NIT is what connects Python code to Yarn. So what this allows, again, Python is a glue. Python can run API jobs, Python can run and connect to run subprocess and lots of other things. So what this allows you to do a lot of things for your cluster. Like if you're struggling to get the full maximum value and performance out of your data in Hadoop and your compute systems out of Hadoop, this is going to really, really help you get tremendous value. So this is just an example showing pandas on HDFS with Dask data frame. Really, it's Dask data frame. So it reads from HDFS. HDFS read is a distributed read, reads on a bunch of nodes. Every one of those in memory constructs a logical data frame, logical Dask data frame in one node. You do the operations at a single notebook as if you're working live on a single machine, but actually what's going on is you're building up a graph of computations. And then when you decide to persist or compute some endpoint in that graph, then it goes off, pushes those, schedules those jobs on all the machines, does the local reads. The distributed scheduler is data local aware, so it only goes to where the data is, minimize the amount of copies that have to take place, but the distributed scheduler will talk between the nodes if it has to in order to complete the job. And you get a result. And it's pandas, it's like pandas working on HDFS directly. It's a beautiful thing. It works reasonably well. So it's still early, but if Matt Rockwell here, he'd be playing it down far more than I am. He's a very humble guy. But it's working really, really well. Question?
So it doesn't touch the JVM at all?
No, does not touch the JVM at all.
So you have to run Dask every single there.
So you run the D worker, it's called. You run the D worker.
On each one of the
On each one of the nodes. Yep, that's right. So NIT is a tool that lets you do that with the Yarn scheduler. There's also other integrations with things like QSub. You can run if you don't have a Hadoop node, you have a bunch of SunGrid engine or something. You can run D worker on all the nodes when they start up as well. That's right. There's no JVM. It's HDFS without Java. Right? So that's the big deal. Yeah.
Do you have to have pandas deployed to all the nodes?
Yes. Yes. You have to have pandas deployed to the node and all its dependencies. Again, something like Conda makes this really easy. But there's tools for doing that are still a little bit. We make it easy with our commercial product called Anaconda Cluster, make it really easy. It's completely impossible to do with other tools. That'll become easier and easier as people kind of, there's other ways to do that. I mean, common is a command I can run, everyone knows. So it's relatively straightforward, but currently that is something we sell as part of our cluster, is making that really, really simple so you can iterate quickly. You just have to do it once, it's fine. All right, so that's kind of the general story. This gets into a little bit of detail of how the HDFS library distributed works. You can do this. You can go and load directly a key from HDFS and basically get the locations where it's stored, and then send those and do whatever you want with it. And so the nice thing about the stack is it's actually very layered. So it's coarser than Spark, right? You kind of go down and you actually see more details than Spark usually hides a lot of this from you. And that has some advantages. It has some disadvantages as well in some cases. But it allows you to build kind of this layered approach. So there's libraries up here that have similar APIs for people who don't want to think about details. If you want to dig in a little bit, you can go and actually make some modifications to make it better. So I know I've spent a lot of time. That's basically what I have. I can definitely take questions as long as you like. But I'm super excited because I feel like, it's really exciting to kind of 4 years later look back and think, man, we did it. We actually got a scalable Python story, both vertically and horizontally, on a shoestring. We did get a Series A in the summer that helped kind of get us over the hump to the last minute, to the last mile. But I'm really so excited. It's never been a better time to use Python data analysis. I think some of these tools will basically show people that invested in learning Python and a NumPy stack and PyData stack will be able to get all the things they want out of their new clusters and all the cluster compute. So I'm really excited about that. Yeah. Sorry, I can't hear you very well. Can you speak up?
It's a totally different kind of question.
Okay.
How do you do when it comes to moving others to make a Python one efficiently work, and not the product, so not over the job code.
Make Python more efficient.
Well, mobile applications.
Mobile applications.
Yeah, what do you guys do to make
you want to write your mobile application in Python.
Yeah.
Yeah, that's the next company. No. It's a good question. I would say one of the web is a mobile. You can basically lets you build applications that deploy to the web. And web applications can also run on the phone. It's not a perfect answer. It's not exactly what everybody wants. Currently, we're not doing anything to make that easier. It is an interesting problem. If anybody has ideas, there was a company just bought by Microsoft for a lot of money. They use .NET. Maybe here, I'll tell you what, if we're really successful, 4 years from now, I'll buy your company if you make one that does mobile Python. But there's a lot of ifs there, right? So.
Hi, I don't know anything about it myself, but the talk of the type annotations that are coming to Python,
yeah.
Is that something that you guys are going to make a lot of use of?
Oh yeah, so thank you. Type annotations. So I had an epiphany at last PyCon when I saw those talking about type annotations. Because I saw how NumPy should have been written and how it could be actually moved to it. So that was very exciting. I would say, of course, their purpose in type annotations is for the linting, the code quality. Be able to basically have lots of people working on big code bases, and then you can do checks, make sure people follow. The thing that people really rely on static languages to get the hints. Type annotations, that's why they're doing it. So you might build linting tools and code quality tools. Now, as a side effect, you will be able to do optimizations as well. We haven't yet done that in NumPy, take advantage of those, but it'll be pretty natural. Just allow, we have a type annotated code and we can make it faster. So, although right now we're kind of doing the approach of having, hey, we have a template, and we just wait till you call it, and then we go type it call it, and then we compile that. Currently, as we do with NumPy, so we allow lots of types. A plus B can be floats, ints, arrays, and when it's called, then it goes generated, or looked up if you've already generated that code.
Just the JIT versus recompile.
Yeah, it's a, well, it's kind of JIT. It's not a tracing JIT, but it's a call side JIT. Good question. Anybody else? Yeah.
I'm just curious if you could share, or if you observed the rate of Python 3 adoption among your customers. Is that sort of?
Good question. I would say, I have not seen it like this. What I have seen is new people coming to Python using Python 3. Right? So it's sort of like what you're seeing is the rate of growth of the Python community. And that's all Python 3. The number of people who have used Python 2 for a long time, I don't see a lot of them converting that quickly. My recommendation is, and I kind of makes it simple, is you can have 2 versions of Python on your machine at the same time. Python 3, Python 2, for it's an environment. You can do both. So don't spend a bunch of time converting your Python 2 code. You can run it. But new code, write with Python 3, and definitely encourage as you maintain your Python 2 code, go back and maintain it and make it able to be used for both Python 2 and Python 3. That's my best practice recommendation. So it's minimally invasive. It gets you in the habit of kind of moving your code gradually to a state where it can run in Python 3.
You mentioned NumPy 2.0.
The mythical. There is no, so I'm not a NumPy maintainer anymore. Right? So NumPy will do what it does. I have opinions about what should happen. My current belief is NumPy needs to be broken up into 3 segments. You have a type system, a ufunc system, and then a container. And the type system, the ufunc system, we could potentially push to get into Python itself. If we did that, then NumPy could be a very simple library, where kind of the computation system is, but the computer sciencey kind of types declaration system, and the stuff that was hard for me as a data scientist and a scientist person to do, and I wish somebody else had done but was doing it. That really should be part of the language, the data declaration system and the function call system. But I was happy to write data approximations to special functions or do your algebra call. That was fine. The other part was hard. So that part really should be part of Python. So how do we get there? The approach we're taking is we're actually building a new C++ library called Dyn, where we're factoring in the verbs. So and then we'll wrap the data creation system in that new one's data shape and make that available in Python generally. So anybody in Python can use it on a function call system we could use. We're heading that direction. If NumPy does, I'm not sure. But the good thing is about the buffer protocol that I also wrote when I wrote NumPy is they can both coexist together. We don't have the same problem. So fix it twice, right? If you have a problem in the community, you fix it twice. You fix the immediate problem, also the underlying problem. You don't have it again.
It's a higher level question. So you mentioned that like a lot of the products, the products that have been open source are overlapping with some certain other products of the ecosystem. And so, I mean, don't you think that's a problem? Because, you know, I'm a user, then I have more choice. And potentially this more choice is not, it gets confusing.
Yeah, so your question is, it gets confusing to have too much choice.
Yes.
That's true.
Well, I mean,
but what specifically are you referring to?
Well, I mean, I can give you examples. So you mentioned,
it's on.
It is. Yeah, so I recently fell in love with Docker. And I also know about Conda. So now I'm looking at these 2 things, and I like some things I can do easier with Conda, and other things I can do easier with Docker.
So I would say those are 2 tools that have overlap, but they're different tools, and neither one does all of the other. Does all of them.
That's right. That's right.
So that's
but potentially you could do everything with Conda, but the thing is, it might be a culture issue. So I can find a Docker image where someone did all the work, so I don't have to do it myself again. So I'll use the Docker.
You should definitely do that. Docker's really good at that sort of thing. But doing things quickly, you still have to be somewhat of a systems engineer to, sort of create Docker images that kind of getting very big. Whereas Conda more about metadata and just storing relationships. So yeah, that's an interesting question. Right now, we use both. We use Docker, we use Conda, and most people we know use both as well. There is, I would say, that's.
I mean, plus, I mean, that's just one example.
The data frame case where you've got S frames, you've got data frames, you've got sparkling pandas, you've got SQL Spark, a ton of stuff out there, right? Yeah, I mean, it'll consolidate. People use interfaces.
Yeah, well, I mean, that's just one example. So I've also seen common elements with what you've shown with like Piano. Piano has this tag idea and it has this.
What is it?
Piano.
Oh, Piano.
Yeah. So it's got this DAG idea.
It does. It's not general purpose computing. It's got a lot of other stuff around.
I mean, it looks like they're trying to push it to be more general, but I mean, that for me is another choice I have to make. Like, should I use Piano or should I use something?
Yeah, there are definitely times you have to make where there's an either or choice, but most of the time it's actually use the right tool for the right job.
I agree.
And that's where open source really benefits you, is because you can. And there's overlap, you're right. You may feel a little bit like the purist might feel like, oh, they're not perfect Lego blocks stacked together, there's more overlap here. But then you get over it and you get your stuff done. It's sort of it's what happens with a federated ecosystem.
Yeah.
Right, where there is no sort of single voice controlling what it's built. It's emergent, right? So any complex math theorist here, there's a covering theorem I always think about. Anyone else here?
Could you say a little bit more about when one would use Dask or PySpark, or are you guys just going to, in a year from now, knock PySpark out of the water?
Yes.
Okay, so you're taking those guys and going and play.
So caveat, more cautiously. If you're using PySpark, I would encourage you to look at that. See if it actually helps. I know that it's not this, there's more tools around like Spark, and so I'm not sure that's not everything. Right, but my guess is, the examples I've seen of people using PySpark, they can get that done faster and more easily and more time way, but it's like that. Now, if you're miles aware, I'm not sure exactly where you're using PySpark.
So do you envision that you just kind of have a marketing problem going forward?
Yes.
Okay.
That's exactly what I'm this is the first time I'm actually giving a talk on this, so I'm just sort of experimenting with y'all. So, and I'm fortunately not the marketing person, but there are other people who do that much better than I do. But yeah, it'll be a marketing. But in a way, Spark's great. It's a good tool, and we use it as well. Like the kind of needs to use Spark. It's not like us versus them kind of mentality. It really is just, again, it brings up this, well, what should I use? People are together and do similar things. And I would say there's enough strength in the story that Dask brings all of the PyData stack to bear, whereas Spark, the image I have are two images. There's the mountain image, two climbers, different sky type, the parallel versus analytics side of the mountain. The other image is PySpark. To me, it feels like you've got this huge balloon you're blown through this little tiny straw of the Spark ecosystem. Right? You're trying to get through it, Dask just opens it up, so you can have this full conversation.
It's all a marketing thing, You might be able to help.
Exactly, that's what I'm hoping. So I'm also cautious, and Matt Walker is really cautious. He's a core developer. He wants to make sure that everyone understands that the distributed schedule is about 6 months old. So, it's kind of rapid progress. And it needs a lot of test cases. These sorts of things need test cases to really iron out.
That's what hackathons are for, right?
So hackathons are for, exactly.
We do that too.
We do that, exactly. So if you try it out, he's anxious for users. He's anxious people say, hey, this breaks, and fix it. I think it's the right approach. I think it's going to be popular because it's faster and actually ties the machine learning we want to do, but it makes it easier. It's not, you have to do a little bit of, you'll have to put those breaks in to do recursive updates, but you can.
We're talking about this ecosystem that G brought up here. So there's all these various options, and I spend a lot of time thinking that something should work, it doesn't work, and then I'm like, oh, why would that work? It's that overflow. Right?
Yeah.
So when is the code going to go, no, put an extra for loop in there?
Error messages be better, you're saying?
Well, it's not an error so much as like a suggestion.
Wow.
It's like, it's not that I did something wrong, it's that like, oh, I see you're trying to do this, why don't you do it this way? Because if you're trying to increase speed, then this will be a lot better.
And you want like a code analysis tool.
How do we get clicking? AI marketing that's actually algorithms from us, right? AI is just a marketing tool that lets me charge $50 an hour.
Look that up and we talk about the money that
Good, yeah, sorry. The linter stuff might help me a bit there, but so speaking of, I guess, Docker, the Apache, everything, are you kind of working towards the use case of all your nodes and stuff being containers in the cloud somewhere, or is it?
Absolutely. I mean, so we have a solution called that kind of cluster that allows you to do that at scale easily. But in addition, we have another open source project called Deck2, which is an example of how to do this on EC2. You can go see how to spin up a bunch of nodes on EC2. Docker I see as an orthogonal story where, yeah, Docker's great, and we can interact with Docker as well. And we'll have, lots of people who build Docker images that contain this as well, and use the orchestration tools around Docker to also spin up the cloud. That's one nice thing I like about the system as well, is that it's a layered approach. You don't have to do all of it. It doesn't try to do everything. It's the piece that you need, and then you have to connect with somebody so the rest of your job done. But hey, that's we'll do it for you if you want. Have a company that will actually help you. But you can do it. We had a question over here. I think you had a question. First. You had a question that you please present.
Kind of peanut gallery questions, but first of all, like I'm thinking about how Dask would change my workflow. So how does it change yours? Like I envision it as like, okay, I've got some nasty extracted data that I'm going to prototype on, and then once I'm done and the code's kind of ready, I'll move it over to Dask and whatever extract.
That's kind of my recommended workflow for the moment. I may change that in a few months to start with Dask, but right now basically just all of the pandas, APIs there, all the NumPy APIs there. You might find yourself, oh, I missed this. You want to do the exploration with this whole pile.
And second, total peanut gallery question, but I have to ask it. All right, I love Conda, I love all your products, I use the hell out of all of it. Why the heck doesn't Conda just fail over to pip with a warning error? Something's not in Conda.
Well, that's a fantastic.
Like, I'm sure there's a great reason. I just want to know what it is so I can stop parsing.
It's definitely been a question that's pained me for a long time. The big answer, honestly, is because, I've talked at length to Nick Coughlin, talked at length to people about this. PIP is a self-integrator solution. So if you're using PIP, you're taking on the pain of making sure that all that stuff works in your machine. So that's compiled, you have to make sure it compiles. If the person didn't get things so that PIP worked on all their machines, on error. So the challenge is, so this is one challenge, making sure when somebody uses Conda, they don't go, oh, it fails over PIP, and it causes a problem, and they go, Conda sucks, right? And they sort of, that's a challenge. Hand off this thing that is this sort of wide open long tail problems. That's one of the things. There may be ways to handle that with right messaging. If you're like, hey, we're going to use PIP now, let's see if we can get it installed. And I think we could do that. One of the things we are going to do over the next 6 months is we want to build a Conda recipes. One of the ways we're going to do that is actually by having a system that lets you build. If you put a Conda recipe together, we'll build both a Conda package and a wheel package for it. And try to kind of get more Conda packages built. So part of the challenge is, while I've really appreciated that PIP has been made it easier for people to get Python, it's also kind of messed us up in the Python world a bit, because it's caused this mental model people have, oh, I've solved the problem, no one does it. Like, I'm tired of it. And so then people go, oh, I've solved the problem, let's keep using it. I won't make Conda packages. Well, if you did, then everything would be better. You'll all be happy with it. Like, there's this interference issue, right? I've talked at length to Nick about it. He goes, oh, yeah, I see your point, yeah. Well, PIP is just a self-integrator, right? You're taking on the goal of being a package manager, a package integrator at that point, using PIP. And Conda isn't perfect either. We can certainly make Conda improve this Conda. But it's a long, someone asked the question of why I should use PIP and PIP install. It's come a long way, I have to admit. It's still not all the way there. It's certainly not where we just abandon Conda and start using PIP. We can certainly integrate with it better. We'll keep working at that, make sure that it's, from our perspective, we'll also keep integrating with our package. People have stuff on CRAN, and Conda will need to interact with that really well too. So it's kind of a general problem to have to be cognizant of and make it easier for people. So, good question, thanks. The good news is you can use PIP with a common environment, but the bad news is like, but I don't want to have to use that. Wish I had a better answer for you.
Could you comment on
the next release will be a graphical manager. Maybe that'll just use PIP behind the scenes. Yeah, question over here.
Could you comment on this is completely different, but on Continuum and the philosophy on making money, but yet having to open source thing? I think it's something a lot of us probably struggle with.
Yeah, everybody struggles with it. They do, actually. There's still an untested question, right? Even Cloudera isn't there yet, right? Cloudera is still living off its pile of cash that they got from Intel. I don't know if it's turned a profit. Hortonworks certainly isn't. Lots of people have this fundamental question, and we're basically living off of investment dollars to see whether or not we're going to be able to make a profitable business out of open source. I've thought about that question for a long time. I don't have the answers. I know that some things work. Doing solutions around open source definitely works. So, if you like a project, you like something that's working, definitely go hire the people that did it to come work for you. First go to them. They may not have time or whatever, but go to them. That actually makes a big difference. It gives them the resources to keep contributing to that project. Definitely, if you're using it inside of a company, contribute to NumFocus. Buy software from a company that's big open source, whether it's Hortonworks or PyData or Continuum. That helps. That contributes. Fundamentally, I think that a company has to sell something that you cannot get unless you pay for it. I think it's just a human nature fact after years of kind of watching this happen and watching, very wealthy companies take open source software and not do anything, just take it.
Where do you draw a line of what to give away and what to sell?
That's a great question. I don't know. My thought is that if it's infrastructure, it's got to be open, because and I think it's an appropriate and healthy balance. If you're going to sell software that is proprietary, you need to be on the cutting edge, because you are going to have open source dipping at your heels. And so basically, if something can be written in a weekend, or it can be, or it's infrastructure that really you need to promote some other concept, that's going to be needing to be open source, right? So you better be looking at what else you're going to be selling instead of that in the coming years. Now, there's always a support model as well, and there will be always a little bit of a percentage of your revenue that will come from support and that'll work. I just don't think it's enough. I think you look at Hortonworks and Cloudera, and the market shows that as well. I think you have to have something to sell. So for the purists out there, the open source purists, they don't like to hear that. But that's the best I've got. 20 years of experiencing this and wanting to be more open source, but realizing that basically you can't just depend on a charity of people to throw you a nickel if they decide that they like your stuff. Like people, and it's not because people are mean or mad or rude or anything like that. It's just because we're locally optimized. Well, I got my own budget, I got my own limited resources, and I've got to make a trade with people. And there's a part of us that'll give, but that's kind of a small percentage. Then they go, I need that to do my job, then I'll pay for it to do my job. So what I like to see is software companies that are selling at the boundary, at the high layer, and pushing the whole infrastructure into open source. I think that's the kind of software company I want to build, and that's the kind I think will work. There's also the software as a service story that's a separate story that we talk about, and that's a model that works as well.
So not to get into the debate between, R versus Python versus R versus Python.
The language wars, they're both great. Yeah, I love R, love Python.
As a long-time R user, I actually have been playing around with New and R and Python in the early days too. And these projects, Spark, and I guess that's what I'm hearing about. I mean, this is like the holy grail.
Yeah, no, I'm excited that actually DAS can enable R users as well.
So
tools I'm talking about.
What do you know of something like this happening, sort of in the art side of the world, or will this support? I mean, where do you see the because they're complementary. Like, so that's the end, they're definitely complementary. One does better, one does better, whatever. I'm just curious as to what you're seeing in the market between.
So I got a chance to work with R and Spark folks as part of the Starfleet initiative. I got a chance to know a lot of R. I've got a little respect for R. I see the value it brings to people. If you're using R, it's hard to say, stop doing that. Use Python. Use the tool you're familiar with. Plus, there's a ton of libraries there. We like to build things that can help glue things together and make it work. The D-worker, for example, can be R. There's nothing. The D-worker is a very simple thing. You can build an R worker. So you can take a graph and actually have it execute R code. It would be an R graph. There's nothing stopping that from happening. So you basically, do the same kind of thing for our collections. That's one approach. That's in the future. It's something you can certainly do with it. I think integrating with dplyr, for example, would be a good example of a way to do that.
I saw a lot of dplyr type firms.
Yes, correct, exactly. Blaze and dplyr have a relationship with each other, right? For example, and so Blaze is going to talk to DAS, dplyr did the same thing. Pretty straightforward. Yeah, no, I like that. Bokeh, our visualization tool, which lets you draw, produce the web, and show that. Peter Wang, my co-founder from Minneapolis tonight, another PyData meetup, they got to see visualization, and that's awesome. He does a great job showing visualization. Kind of get analytics if you were me. R Bokeh. What's really cool is there's a native R wrapper, so you can write R code and have it show on the web. So R Bokeh. So we like to help data scientists using whatever mechanism they like. Well, it's great. I think probably ready to go to drinks, right?
Yeah, let's give a round of applause for Travis. As mentioned earlier, we'll have our drinks at Tonic. I want to mention two things before we get out over there. What's the best way to get in touch with you and your committee for planning the conference?
Yeah, so I think the best way is if you can reach out to the organizers of the meetup event on the site. Alternatively, you can find one of us, it's Happy Hour or anyone from Capital One. And I actually want to really quickly mention one other thing on that note. We mentioned earlier kind of briefly that Capital One is was sponsoring this event. You may know our credit cards are our bank, but what you may not know is how near and dear data science really is to our heart and our face, actually in the DC area, right by the McLean Metro Station, McLean, Virginia. Just really quickly want to mention that something that we really want to do is kind of get closer to the DC community overall. So thank you so much for kind of letting us sponsor this and be a part of this. And then finally, I'm super passionate and excited about kind of full-scale PyData event. I thought this was really exciting. Be on the lookout. Hopefully that'll happen in the fall. We're thinking maybe October. Please do kind of reach out through the meetup group or to anyone you meet at Happy Hour later tonight who's kind of involved and help us make this as great as you can. And really the kind of conference you'd be really excited to go to.
Awesome. Thanks again, everyone, for coming out, and see you all at Tonic.